tackle the idea of resonance. Resonance structures are, well, let me draw the Lewis structure first, and then we'll talk about resonance structures. So this is HCO2 minus, and another way of writing this would be HCOO minus. And yes, and it says carbon is the central atom, meaning that both of these oxygens and this hydrogen are all bonded to the carbon, and we need that hint to make sure that you don't try and attach a carbon to oxygen then to another oxygen. So that's a hint. Let's add up our valence electrons. We have 1 plus 4 plus each oxygen has a 6, and then we add 1 more for the charge. We end up with 12, 16, 17, 18. And perhaps you're noticing a pattern in that at least every single Lewis structure we've done so far, and the vast majority of them that we will see, have even numbers of electron. And that comes about because they all end up in pairs, because each bond is a pair of electrons, and each unshared pair of electrons is, or lone pair of electrons, is a pair as well. There are very few cases where you will see odd number of valence electrons. If we don't see one today and it shows up on the homework, please ask. I don't know if it does, actually. But if it does, we'll deal with it. So if you get an odd number of valence electrons when you count them up, recount to make sure, because it should be almost always even. Now we have 18. Put your carbon in the middle. We know that because it told us, in case we did not know it. I have 18 valence electrons total. I've already done 6. I don't need any more valence electrons around my hydrogen. Hydrogen only ever wants 1 bond. And these 2 electrons shared give hydrogen the same valence electrons as helium, its nearest noble gas. So this one's done. So I go to my oxygens, 8, 10, 12.
Professor, I have a question.
Yes.
Do the other matter, can you put the oxygen from the beginning where is the hydrogen?
Oh yeah, you can put them, so there are many, so you could do this. You could do, I mean, it doesn't, as long as you have all 3 of them bonded to the carbon, they can have any layout you want.
Okay.
Yeah. Because what's important for Lewis structures is not, well, let's say this, is not the positions of the atoms. It is that all bonds are shown and that all pairs of electrons are shown wherever they are. And when we talk about resonance structures, there will be one thing we will say about position of atoms, but otherwise, no. So I have my 18 valence electrons in here. I can see that my oxygens, each of them has an octet, and my hydrogen is happy as well. But my carbon does not have an octet, which means that I need to form 1 double bond. And here's where resonance structures come in. Resonance structures are going to come in when you have a choice where to put the double bond. You end up drawing all possibilities. But for now, let's just do one of them. It doesn't matter which one you do. Take 1 pair of electrons, form a double bond. That leaves us with a double bond to the oxygen and a single bond to the other oxygen. And now my carbon has 8 valence electrons around it. There must be a negative formal charge somewhere in here, at least, although probably at most as well, because there's a negative charge on the whole thing. If we do a formal charge analysis on each of the atoms, and we might as well do it because we need to get good at doing formal charge analysis, I now have 2 oxygens that are different from each other. Each oxygen will have a different formal charge. So the oxygen down here each oxygen has 6 electrons from the periodic table, valence electrons. And this oxygen has 2 bonds plus 1, 2, 3, 4 unshared electrons. So the formal charge on this oxygen is 0. The formal charge here six valence electrons from the periodic table minus 1 bond and 6 unshared electrons. There is our negative formal charge. Put it in a minus in a circle right next to that oxygen. And if we now do the carbon here, the formal charge on the carbon says carbon has 4 valence electrons from the periodic table. And it has 1, 2, 3, 4 bonds plus 0 unshared electrons. 4 minus 4 is 0. Good, because if we ended up with a formal charge here that was other than 0, our formal charges wouldn't equal the charge on the ion.
Professor, I'm sorry. How do you get negative 1 again, please?
Oh yeah, my pleasure, Monique. Yeah, good question. So on this oxygen, the formal charge on this oxygen start with 6 valence electrons from the periodic table. Subtract off 1 for the 1 bond. And then, just to be clear, this means add these up and then subtract them off of the 6. That's why they're in the square brackets.
Well, that's not positive 1, or that would be negative, because when you add it up, it's 7.
That's right. So it's 6 minus 7.
Oh, okay.
Cool. Yeah. And then just to complete this 6 is the number 1, 2, 3, 4, 5, 6 unshared electrons. But yeah, so this means add these up, get 7, subtract them off of the 6. Cool.
Is that in the lecture you had labeled the different oxygens, like oxygen A or oxygen B?
Yes.
Is that one that is it? Will we call that, or we just kind of point to the arrows, or does it matter?
So any way you have of doing it that tells me, like, so after you do 10 or 20 of these at some point, you'll do you can do the formal charge analysis in your head and just put the formal charges. Like, you don't have to show me all this. Only show it to me if it helps you do your process. But
we're not supposed to do it on hydrogen?
You can totally do it on hydrogen. Hydrogen has 1 valence electron from the periodic table, and it has 1 bond and no unshared electrons, so its formal charge will be 0 as well. But we typically don't do hydrogens because hydrogens are always 0, by the way. But there's nothing wrong with doing it. All of these rules definitely apply to hydrogen as well. And what you were commenting on is I would do oxygen A and call this oxygen A, and oxygen B and call this oxygen B. And those are fine. The only reason I didn't is that I pointed to them instead is sometimes the A's and the B's can clutter up your Lewis structure a little bit, but however, like these are all, as you know by now, I imagine, and I know we've worked a lot, Michael, is so when you just need to show me your process, or let's say this, you need to show me enough so that I understand what you did. You can use the A's and the B's, you can point, you can do both. Whatever helps you is where I am. So.
Okay. Prof, can we equally use 1 and 2? 1, 2, or 3? I know I have a question like that in question 1.
So you, and Kiro, you have a question about question number 1?
Yes, I said this particular one you're trying to explain where we have two different unshared elements for oxygen. I said we have such question in question 2. Question 2 where we have oxygen, 3 oxygens. So I said, can we just assign, as you said, we can assign A, B, or whatever to it. Can we assign like 1, 2, 3 to it?
Yes, you can. Yeah.
Okay.
Yeah. That would be great. That would be fine with me. That'd be great with me, actually. Any other questions? Because we're still not done, but this is, I mean, you can see we always start by doing a Lewis structure, then continue with a formal charge analysis, and then we still have something left to do for this problem. But that's always how it goes. And that's why Lewis structures are so important, is because they form the basis of almost all of our steps from now on. And certainly everything we do today. Okay, so but hearing nothing, so where we are right now is this is our best Lewis structure. And I'm just going to write capital L, capital S for Lewis structure. This is our best Lewis structure. And now we have to think about resonance structures. And what we've said about resonance structures so far is that whenever you have a choice where you put the double bond, we put it here, but we could have put it here. You draw all choices. So let me do that next. Resonance structures. I'll put down here. So there will be 2 of them. One will be just like this. And then this arrow with 2 heads on it is called a resonance arrow. Resonance arrow. You don't have to draw it, but it is typically done. And now I'm going to draw the double bond in the structure over here. I'm going to draw the double bond here and the single bond down here. And for resonance structures only, you do have to draw the atoms in the exact same positions. So you have carbon, you have to have the hydrogen to the left, the oxygen to the right, and one of the oxygens going down. And I'll zoom in a little bit to show this, even hopefully a little better. But now the double bond goes to the right and the single bond goes down, and you can see that all of the atoms are in the exact same positions for resonance structures only. And then you fill in the electrons. If this oxygen has a single bond, then it will have 3 pairs of electrons. And if this has a double bond, it will have 2 pairs. And the formal charge of minus will be down here. And this is your final answer for this, by the way. Oh, we still have more to do, by the way. Sorry, there's more to this final answer. But those are the resonance structures. And the take-home message is, whenever you have a choice where you put a double bond, draw all choices. Whenever you have a choice where to put a double bond, draw all choices.
What about the bond order?
Yes, no, that's where we're going next, Michael. Good question. Thank you. Okay, so then now let's talk. And the question, by the way, I can zoom back out, says, and describe how these structures relate to the true nature of the carbon-oxygen bond. And that deals with bond order, which is what I want to talk about next. And let's see. Okay, so now we've got our two resonance structures. And now let's talk about the true nature of the carbon-oxygen bond. And what we can see, and the way you approach this is, you circle the same carbon-oxygen bond, and that's why it's important that you place the atoms in the same places. So I can see I have this carbon-oxygen, the oxygen to the right, and I've circled it here as well. And then what you're going to do what's called the bond order is you calculate the total number of bonds, which is 1 plus 2, but I'll just write total number of bonds, divided by the number of resonance structures. So I'll put number there, number of resonance structures. And if you do that, you'll see this carbon and oxygen have 1, 2, 3 bonds over 2 resonance structures, which is 3/2, which is a bond order of 1.5. And bond order's abbreviation is B, capital B, capital O, because Gen Chem has BO. Now, so this is the bond order, and now the last thing we have to talk about is what this means. So a bond order of 1.5 means that this bond is halfway between a single and a double bond. So the carbon-oxygen bond in this structure, which is HCO2 minus, is halfway between a single and a double bond.
You said that single bonds are longer than double bonds?
That's right. So if we were thinking about what it means to be halfway between a single and a double bond, a single bond is longer and weaker than a double bond. So a single bond is longer and weaker than a 1.5 bond as well, and a 1.5 bond order is longer and weaker than a double bond. So if we were going to then go and say, okay, so longest and weakest would be single. Then you'll see a 1.33, a 1.5, a 1.66, a 2, a 2.33. These are all possible. And then a 3 bond order. And this over here, which would be a triple bond, would be the shortest and strongest. Because a triple bond amounts to 3 pairs of electrons shared between the 2 atoms, and that creates a very strong bond. Now let me zoom back out a little bit. I'll just say one more thing about this before we go on a break, although I'm happy to answer any questions you have about this problem before I go on break. So we talked about this bond here between carbon and oxygen. If we had talked about the other one, we would see that it has exactly the same bond order. And we could say this about the other bond as well. And the last detail that's important about this is that both of these bonds are bond order equals 1.5. There is no difference between these 2 bonds. And that's why we do resonance structures. The reason we do resonance structures is because if you look at just this, you might think that there's a single bond and a double bond in this molecule. But when you look at resonance structures and then you do the bond order calculation, you see that both of these bonds are actually bond order 1.5. Both of these bonds are identical and there are no differences. So on your exam, if there's a question that says in HCOO, are there single bonds, are there double bonds, or are there 1.5 bonds? The only bond that exists in this molecule is a bond order equals 1.5 bond. Phew, we've tackled a lot today already. Are there any questions about this before we take a break? Okay. Well, then we're going to take a 10-minute break. It's 9:42. Let me stop the video, I guess. It's 9:42.